Can you hear me?
Yes, sir.
Thank you. Okay, let's wait for like 5 minutes, then we can start. Today, maybe I'll just like show some how like run through of design builder. Since actually there was a detailed class lecture on how to design shading devices, I thought I'll give a small run through of design builder for a longer time. Then I'll just give a run through regarding sound. That's how it will be. Other than that, like how was this week? Good evening, everyone. We'll just wait for a minute or two, then we'll just start the session. Okay, let's let's start the session. So this this session will be about week number 3, which covers shading device design, about building energy simulation, and also about sound. Since shading devices and how to design shading devices was explained in detail with Ecotech, uh, I'll just like move further to design builder. Like I just took one single simulation software. Maybe I'll just give a run through how it is done. Then I'll talk about sound, and there might be one single example and some values which we come across related to sound and what are the noise criteria. And finally, you can also ask doubts. Also, I'll ask one of my colleagues also. He is an expert in sound. If you have any doubts there related to sound, also you can ask. Moving further, like I'm just like going to the last week what we ended. Like we talked about uh, heat transfer, thermal efficiency, like with the help of envelope, thermal efficiency in glazing, and also how the shading device and shadow angles work. And moving further, uh, in week 3, the first class, you would have come across how to design shading devices using Ecotech. And next, I'll stop sharing and then I'll share another window. I think I have to share my entire screen now. Let me share. Here, I'll just give a very small demo about Design Builder, how to like do a small building performance simulation. Here I already opened a new file. Like you have to click here, create of new file, and further you will be asked about. Maybe I'll just create a new one. Basically, this is Design Builder, and it is based on the Energy Plus engine. Energy Plus engine is a free open source energy simulation engine, and Design Builder is some kind of a wrapper which utilizes the engine, and then it has more libraries included, predefined libraries, so you can like it is more user friendly. Here, once you give new, you will be asked which is the location and what is the analysis type. Here, the default is Energy Plus, and you just give a title of your project, whatever it is. And here you have the option. By default, there are few locations available for India. You can choose one among them. I have chosen Indore. If you don't have exact location of your uh, the place that you are going to simulate, you can always go into, maybe I'll share another website. One is Energy Plus. You go into Energy Plus, there will be multiple weather data files available. And another one is on climate. Correct me, I think it's, if you Google search, you will get it. There are like multiple station data that are available. You can utilize them and then use them for simulation. Once this is done, it will enter into the drawing window, like the layout window. Here you have to like go and select this add building option. Home with plus symbol will be there. That you have to click. There you have to select which type of building that you are going to use. Like this might be an office building, this might be a school institutional building. So here you go there and then you can choose which type of building, either it's like main differences in residential, non-residential, is it a new building? These kind of things will help in, like, there are multiple uh, tools that are available in Design Builder. Here we are mainly focusing on thermal energy simulation, because other things there are like daylighting, CFD, cost and carbon analysis. All these things are there available in this software, but we are currently just focusing on the building thermal simulation. Moving further, you just click OK. Here basically it's almost like SketchUp. You just draw walls and then define the openings and define zones, and you have to define the construction material which you are using. Once you like define what just the thermal envelope, we need not look into, there are multiple factors actually that affect building energy, which like the system sizing and also the occupant, how they are using it, the occupant behavior, and what and all internal loads that are there. So these things we don't cover in this session. You can look into further. Actually, you can. There is a separate YouTube channel which in full tutorial. There's a full whole tutorial on Design Builder. You can check into that also. Design Builder, you can also get a trial version for a few set of days. If you want to look, try this out. Basically, you can just, here there is multiple snap options also available, where you can give this snap increment. It helps you, like if you want to give defined exact dimension snaps. Let us just draw 5 by 7 building. Now it's like a building will be like automatically defined. This is because once you like select the building level, and also when you're drawing, you have to think in terms of which level you are working on. It works in a hierarchical basis. If you make any changes at building level, it will be reflected below the below layers totally. But if you go to one particular wall and then change it, it won't be reflected in the above layers. That you have to keep in mind. I'll go back into the building level. And a main factor, just considering the building science, is the envelope part. Here you can define what and all wall material that you can choose. Here I'll just choose external walls as solid brick wall. This will be actually reflected in all other walls. If you select that, you will be able to see. A similar way, you can select the roof, the ground floor, below floor also. And next is, by default, you can define the wall window ratio also, or else you can also have the option to draw exact opening size by selecting the wall, going to the layout level, and then you can draw the openings. Here we just define wall window ratio. Here I have defined 10 now. Once I have defined, you go back to the layout level. Now you can see that the changes have been incorporated. Other than that, there are multiple things. Here uh, there is a separate section called as shading. Here you can give default shading. The window shading actually means the internal shading, but what here the actual shading device, here it is the local shading device. Here you can, there are several libraries you can choose from. Also, you can also make a copy of it, and then like this example, like you have already analyzed what type of shading device you are going to do using EcoTech. You can like kind of you use the same dimension and then incorporate it here. I'll just like, now I have created one copy. If we go to edit, here there are like multiple options. You can select what type of material that you are going to use. Now we'll just leave it as default. So this is where you can like give the side fin if needed, if you need a overhang of how long it is. So give OK, you select it, make sure you select it. Now you go back to the layout level. You can see a wireframe kind of drawing which shows how the local shading device is. Moving further, these topics is not covered in the whole series, so I'll just like switch off the heating cooling components. And there is one more thing, activity which I was talking about. Here you define what is like expected number of people in the room. It can be defined in multiple ways. Here it is, the option here available is people per meter square. And you can also select schedule. Here imagine that this is a living room, residential living room. There are default templates available which you can choose from, or else you can also edit the same. Whatever library available, if there is an option to edit it, you cannot edit it directly because it is the default library, it will be logged. But you can create a copy and then further go and change just to check the reference. Like now you can see the occupancy area. This is how it is written. It's like this until 7 means it's like until 1 means actually it is like it is full occupancy, and 0.25 means like 1/4 of occupancy, and 0 means the space is not occupied at all. And this you can define like what is the occupancy during weekdays, what is during holidays, what is during weekends. All these things you can define, and there are multiple ways you can define also. Like one is schedule, like across months and the particular day how it is occupied. And this compact schedule is more customizable, even though it is little bit hard to do. Once you have defined the occupant schedule, there are multiple things. You would have come across clothing and metabolic rate, which was spoken in the week 1, which affects the thermal comfort of a person. So the activity level is used to, in this simulation, it is used to find the PMV predicted mean want also, and also same metabolic rate will also be used to find the internal load. Since there is a particular activity happening inside a space, there will be some kind of energy which will be released from the body. This will add up to the internal load, which will be like further adding into the cooling load. So this also will be used, and further clothing is also used in PMV calculation. Moving further, you can also define whether there are like equipments apart from lighting. Like even lighting, you can define what is the type of light used, what is the power density. All the things will be used in lighting also, and also in the internal load calculation. Once all things are set, you go to simulation tab. Here you give update data, and you also select what is the duration you want to actually simulate for. Let us like try to simulate this room during the typical winter peak duration. Here you select what are the outputs you want. You can get monthly outputs, daily outputs, even sub-hourly outputs. Yes, sub-hourly thing, these things I'll show it back where it can be set. Let us run the simulation. Now you are getting the outputs. Now let me change here this bottom portion, left bottom portion. This is where you can select how you visualize the data. Before it was daily, now I changed it to hourly. So you can see the performance, thermal performance of the house over a week. Here, this dark blue line depicts the outdoor air temperature, and the above three lines, these are like air temperature, radiant temperature, and operating temperature. Since it's a winter period, the air temperature is little bit above the outside air temperature. The bottom portion shows the fresh uh, air exchange during the time. Also, the middle portion, this chart shows the heat balance, how the heat balance is happening. Like here, this light green color is showing the heat balance is in the negative direction, which means the heat is being kind of removed from the space. Apart from the external infiltration, all other portions exam. Here you can see the general lighting, computer equipment, occupancy, and solar heat gain. All these things add up to the internal heat gain. And also you can, for example, if you want to check what is the surface temperature, you can also check into it. Only thing is you have to like select what and all the output that you want. And so this is kind of an overview. There are like so much things that has to be like discussed in detail, but since it's a limited time period, I'm just giving a overall run through so that like you can explore further. This button actually is the overall model setting, option settings. You can set things like what is the HVAC, how the HVAC is actually calculated, either it is simple or detailed design, and how the ventilation and infiltration is calculated. All these things you can set here. And then under simulation, you have this time steps also. Here time steps means if you define it as like 2, it means that the simulation will try to calculate the outputs. Here it is defined as 2, it means that the output will be defined every half an hour. And if you move further, if you give like 6, you can go up till 60. 60 means that every minute you will get the output for sub-hourly calculations. I think it's, oh, we can stop here related to design builder. There are also other tools like here design builder, there is an option to find the day lighting. Maybe we can see this in the next week where the portion is on acoustics and also lighting. I'm just kind of showing a small visualization how the lighting is. This is how this is like illuminance at a particular time period, and this is like annual day lighting, which we can discuss later. If you have any doubts related to design builder, you want to like explore about it, or any alternative software that you want to ask, you can ask now. Let me just close it. Further, we'll move on to sound. So here the whole course, it has been like split up into 3 different parts. One is like thermal, next is now this is sound, and the last one is lighting. Like there is thermal comfort, there is also acoustical comfort that people should be aware of also. And there are so many criteria that as an architect or an engineer we should be able to know how to design them. So speaking of sound, basically sound kind of travels through a medium. It basically requires some kind of medium to actually travel. It cannot travel in if you have a vacuum space, sound cannot be able to travel, and it depends on factors like density, temperature of the particular medium. So to like in order to find how fast sound can travel, is these medium based parameters like density and temperature, they do come into play. And in general, sound pressure is actually measured in pascals, but since sound if you take human perception, you can hear the Pascal of like 0.00004 till a larger Pascal. That's a very long range. So in order to find a relative range where you can define sound, it has been defined based on sound pressure levels. When you talk about levels, it it is defined based on the unit called decibel, and this bell actually has been named after scientist Alexander Graham Bell. And speaking about sound, there are multiple uh, parameters that, that are involved with sound. Sound can be measured in terms of power. Here, the sound power is basically the source, like the point source. In when we talk about thermal simulation, it's the source, emitted source, we call it as sound power, and also intensity. And sound pressure is something like you what you receive it, and you would have come across all these formulas discussed in the last class. Moving further, and also the class covered interrelationships between sound power, sound intensity, and pressure level. Some pointers you try to remember is like sound pressure is almost equal to sound intensity level. And speaking about this, the first formula talks about intensity can be measured based on the sound power divided by 4 pi r square. Here the 4 pi r square is basically the unidirectional spherical globe that you have to consider. This globe, imagine you have a point source, and then at any particular distance from the source, you will have a uniform receiving of sound intensity level, which can be defined using this formula W by 4 pi r square. Imagine if you have like 0.005 watts, and then implementing the distance and also the watts, you will get a intensity SI unit of watts per meter square. After we convert it into a comparable level in decibel form using the logarithmic equation, and we are ending up with 80 decibel. Here, two major pointers you have to think like there are obviously we cannot remember so many formulas in our head, but some basic intuition that you have to can get from this is that the sound level actually drops by 6 decibel whenever you double the distance. And moving further, the next formula is the relationship between the sound intensity level and the sound pressure, and it also depends on the density and velocity, which is called a specific acoustic impedance. And in order to find what is the sound level, pressure level from a particular distance, imagine you have a point source, and then from a particular distance, what is the pressure level based on the power, you can use this formula. And the right side diagram, what you are looking at is the relationship between pressure and also the intensity. Moving further, one thing we talked about the point source sound and what is the sound intensity level that you will get. And next thing talks about, imagine we have two equal point sources next to each other and they are of same sound power. So they will need to increase of sound level by 3 decibels. Whenever you have equal sound source, two equal sound source, the decibel level will increase by 3. And this small example covers about, imagine there are like multiple sound sources. We have an alarm clock, we have an electric shower, there are like two vacuum cleaners that are functioning, and then side by side there is garbage disposal happening in a room. In order to find this total sound level, you have to compare what is the decibel level of each source. If you have equal sources, here we have two vacuum cleaners which are functioning at 79 decibels sound level. So since they are two equally sound sources, we add up 3 decibels, which can be calculated in this manner, but this is more like a thumb rule. We just go add 3 decibels, you will end up getting 82 decibels. Further, we look into other sound sources. Here the alarm clock is at 62 decibels and the electric shower is at 60 decibel. And since they are almost equal, if there is a difference like +9 difference between two sound sources, you just neglect everything and then select which is the highest sound source. But you have almost equal, in this case alarm clock and shower. If you try to calculate it, you will kind of end up having an addition of 2 decibels. That's what here it led to addition of 2 decibels, and then the alarm and shower together resulted in decibel level of 64. Finally, we just compare everything anyway. The vacuum cleaners, two vacuum cleaner sources, they yielded in the highest level of sound, which is 82 decibel. We just have to take that. And moving further, you would have come across this linear equivalent sound pressure level, which is used as what is the average steady noise level over a period of time. This can be utilized to check whether one single space, using measurements, that is the space actually noisy, is it within the limits, noise level limits. But this LEQ gives a overall average throughout the time, and it's a single remainder, but there are other values like L10, L50, L90, which can be used to give more insight, further deep insight into how the noise levels in multiple manner. Like L10 actually gives what is the highest sound pressure level exceeding over 10% of the time in that room. So using L10 and L90, you can kind of gain more insight. Example, we have like L10 is around like 70 decibels and L90 is something around 50 decibel. It means that just for a smaller duration of time, the sound level exceeded to 70. But L90, since it is like 50, it's like you can consider that on an average, the whole space is kind of acceptable if the acceptable decibel range is below 60. This formula you would have come across. This is for this is used to find the sound pressure level at a point, And if you if you have a single source point, like you have one single source and then there are like two different points from that source point, in order to find the difference between the sound levels between the 2 points, you can utilize the below formula to find out what is the sound pressure level difference between the 2 points. The same way, if we have a directional source, there are factors that we have to consider if we have a directional source. Here, directional, the point we are speaking, you would have been explained that if you have surfaces nearby, like non-directional source means that it's kind of in a vacuum, like in space there is one sound source. It kind of like be emitted in all direction. But in real cases, imagine you are standing in a plain ground. That defines something like this second image. This maybe a person is shouting from a plain ground. This is another case where you are shouting from an open air theater. The last one is like maybe imagine that you are shouting it from a corner of a room. This will lead to, due to the surface nearby, there is a addition of the sound level due to the source. This phenomenon is directivity, and directivity is, there are simple values based on the configuration of the space. You can use this value further in this equation. Here the Q is actually directivity, and I theta is the intensity at a given angle. W is the power, as you know earlier. And here, when you look at this, there is a small correction in the sound pressure level when we look into directional source, where you include this I and directional directivity, I theta and directivity into the calculation of sound pressure level. As of now, we all spoke about the sound pressure level, and actually when you speak about sound has multiple frequencies, like you can receive sound with multiple frequencies, and this matters a lot because each source has different types of frequency output. Imagine if you have a pure tone, this tone will have one single frequency with one single sound pressure level, and we take into the account of musical equipment, harmonic equipment like a violin. You will have specific number of frequencies, like different bands, you can say, and each band will have its own sound pressure level. And we go further into real world situation like operating of fan, it will lead into a more complex sound output with different frequencies. Here you can see, like, this is the spectrum of the frequency resolution. Here you can see it's just one single frequency point you are getting this output, but in harmonic instrument you have like some several frequency points that you have. But when you go into real world situation, you will have a complex mix of frequencies. And the last chart where you look into, like, you would have been explained about dBA, where A stands for like how the human perceives the sound as for different frequency ranges. Example, if you have a very low frequency, the same output, decibel output, what human perceives will be actually less, which is actually indicated with this dotted line. The dotted line defines the actual decibel level, but the solid line actually is the perceived, human perceived, or A weighted sound pressure level. and it also has different ranges. Example here, this fan noise, it even though it produces higher decibel level at lower frequencies, the perceived noise is sound pressure level is actually very less. Moving further, noise is something very subjective, but there are particular norms that we can follow to define noise based on indexes. This one is a noise criteria, it's an index where for specific zones, what is you can define limits. This noise criteria is it utilizes the combination of this frequency and also the pressure level. What we saw last year for different frequency range and pressure level, there are curves that has been defined. Here, this light gray lines, you can see these are the noise criteria lines, and these are example sound outputs that actually happens in relevant conditions. Imagine you consider this topmost one, which depicts a loud stereo playing in a living room, and it exits beyond NC 70, which is noise criteria of 70. When you look into this NC 15, which is basically a mechanical system off in a quiet mode in a hall. So these are actually these dark black lines, what you see are basically the measurements that have been taken, and using the measurements you can actually compare it whether it is acceptable or not. There will be some criteria. As example, if you have an office space and then you have sound pressure is basically measured in the normal context. Now we measure in decibels, but it is sound pressure level. Here you can see, right, it is sound pressure level. That's for normal understanding. We use it conventionally, we use sound pressure level to measure the sound, but just when you say sound pressure, it will be in Pascal, but we don't use it, just you take it as sound pressure level. And next, moving on, we as of now we all looked into how the sound, we talked about the sound pressure level, frequency, all these things, but we didn't speak anything related to time. Now sound travels at a particular speed, and there are many things that we have to consider when you look into sound in a closed space, because after a certain duration of time, fraction of time, sound starts getting reflected. Imagine this diagram shows that, imagine there is an omnidirectional point source at time 4 milliseconds, it reaches a small distance. Imagine it's like 0.5 meters. Further, plus 8 milliseconds, it reaches a distance of like more than 2 meters. Imagine if you have a 3 by 3 meter room, it kind of like the point source it hits a surface and it starts getting reflected. So after certain duration of time, there will be multiple reflections, like it starts bouncing everywhere. This bouncing is phenomena happens in terms of like radiation, and also in lighting. You will, when you look into, there are so many things that come into play both in this context and also in lighting also, where you can use this inverse square law also. Here, when the main thing, the what I'm trying to say is the reverberation time, which you have to think when you design spaces. Reverberation time basically is the time required for reflection to decay. Basically, if you have one point source, so this point source is an instantaneous source. You will have multiple sources, like over a period of time. Example, if I am talking, one word that I spoke will be like in the space due to reflection. It will be still in the space. You have to make sure that some sounds which are not desirable to die off sooner or later, because when we have a space like a meeting room where you all the thing that happens is conversation, people conversing among each other, you should like the space should be designed in a way that the reverberation time is as low as possible. But if we have a space like a concert hall or music performance theater, since it is a large space also, there will be a bigger reverberation time, and it is also acceptable in that condition, because like you have a music being played, the music stays for a while. For you to experience, it should be like extended for a small duration of time. That we can look into. You can give a further reading. Maybe I can recommend you a book also. Let me look into it. There is a book called as Architectural Acoustics Illustrated by Michael Ehrman. It's a Willer published book. All these diagrams which I showed in this presentation, I have taken it from that book only. And now let us look into as a small example how to find reverberation time. Reverberation time is basically depends on the volume of the space and also the area and also surface characteristic of each surface. You have to take into account what is the surface characteristics in terms of sound absorption time. Sound absorption coefficient is something that takes into account how much of the sound is being absorbed by the surface. So if you have like here I have taken a room of 5 by 4 meter with height of 4 meter, and the walls are having a sound absorption coefficient of 0.6, and the floor is having 0.3 and the ceiling is having 0.4. This means that the wall has a more absorbing surface and the floor is very low. Ceiling is kind of a medium absorption level. Since it is a very small room, you can comparatively compared to a concert hall, it is a considerably a small room. You won't have much of a acoustical issue in this space. Next, how to find this A, which is Savins. A is actually Savins, which is a summation of the surface area multiplied by wall absorption coefficient. Here A1 is basically the Savins for all the walls. I have used this formula, and then you find out what is the actual A value. Now it has been like equated as like 57.2 meter square, and volume is basically 5 into 4 into 4, it's basically 80 meter cube. Now you use this RT calculation formula, and you sorry, I have some connection issues. I hope you can see the screen. Moving further, to calculate the RT, you just implement all these values in the formula, and then you are ending up getting an RT value of 0.29, which 23, sorry, 0.23, which is very good. value if you consider this room is being used for conversation purpose. If the RT value is the same for a space like this concert, it won't be good. Further, let us talk about this absorption coefficient, how these panels are like these elements, basically how building elements lead to absorption coefficient. Here, when we talk about this porous observers, is example a porous absorber material, like glass wool is being pasted on the ceiling. This will yield an absorption coefficient like of around like 0.8. But if you use something like a banner, you would have seen these kind of hanging panels in auditoriums. Basically, these are more a kind of an effective way to use the acoustical material because both side of the material is being used to absorb the sound. Further, you look into another example where you have a thick glass fiber flushed wall. Another one is you have battens and then over the batten you have a board, kind of a panel. Imagine this a gypsum board panel. And this is the absorption coefficient. Another thing you have to main thing that you have to look into is this, even this absorption coefficient, it differs. The value differs for different frequency of sound. Example, this black line actually defines this panel absorber. It has a very good absorption value of 0.75. When you have a frequency like around like 100, this is an Octavian band hertz. But when you look into this glass fiber, it has better absorption coefficient values at higher frequencies. So in order to design a room, you have to look into what is the sound source, what is the purpose of the room that is being used, and what is the materials that you have to choose. All these things you have to consider when you go to designing your space in terms of acoustic. So I think this is my last slide. This gives a list of materials and their corresponding absorption coefficient values at different frequencies. Imagine you have this gypsum board. It has a absorption coefficient of 0.29 at 125 hertz. But when you go further at higher frequencies like 4000 hertz, it's having a very less value of 0.09, which is too low to be considered as a good absorbing surface. But when we look at this good absorber like a soft porous fuzzy material like glass wool or something, glass wool, rock wool, all these are like sound and thermal insulative materials. When you go into like insulation, you can like think in terms of how it is thermally performing, acoustically performing, and there is another thing that you have to consider is fire safety. Example, you have very good thermal insulation and also very good acoustic insulation, but if it's not, it's a poor uh, material against fire, it's not a good option to use. So all these things you have to take into account when you are going to design the building. So this first you're seeing, right, like here the example material like glass wool, it has a almost lesser absorbent coefficient than a gypsum board panel at a lower frequency. But when you go further into this higher frequency sound range, it has a very good performing absorbent coefficient of 0.95, 0.85 and all. So you look into the actual sound source, what range, what is the high frequency range that sound source is giving, and select the material according to it. So with this, I'll stop my presentation. Now you can ask any doubt. I- We can, you can switch on your mic, you can converse. It's not, if possible, try to do it. Or else you can type question in the chat also. Also, you can ask about any doubts apart from this class also, like anything related to building science or anything you want to know about, like any software that you want to explore. You can ask all these details. This session is basically supposed to be a doubt clearing session because since NPTEL is an online course, there is very less chance of interaction. So this current space gives you good place for an interactive session. Second assignment. Can you mention what is the assignment? You can speak, switch on your mic and ask. Is it related to sound or is it related to thermal performance? I think it is related to thermal transmittance, I remember. Seema? Okay. What's the question? Maybe I'll open it. Let me open. Yeah.
Yes, sir. Just wait. I'm just opening through the assignment.
Yeah,
Okay.
you can also share the screen. The
Yes.
submission has been done,
Yes,
right?
sir. Yes. Just 2 minutes.
Okay. Let me also log in. Other than that, anyone else? Okay. Okay, I can see this whole section of 3. Let's take two. Let me also log in. Give me a second. So basically, this is matter of how you find the,
Sir.
yeah, basically
Um,
you have to find the individual resistance.
sir, is my screen visible?
I can't see your screen, Seema.
Okay. Shall I read the problem?
Yeah, I saw in chat. Is
Yes.
that the
Determine
one?
the U value for the following wall section composed of
Uh-huh.
three
Uh-huh.
cardboard, 1 by 4 inch thick, expanded polystyrene 2 inches thick,
Uh-huh.
plywood
So
3 by
here,
4
here,
inches
here,
thick.
no, it's a very simple calculation because the resistance have been given directly. Resistance per inch has been given. Okay. All
Okay.
you have to do is multiply the resistance per inch into the actual inch value of each material. Example, you have hardboard of 1 by 4 inch thick. You multiply 0.25 into the hardboard resistance value. Hardboard is 0.18. You just, it's like same like this Sabin's formula what you saw, right? You summate all this thickness multiplied by the resistance value, and
Okay, sir.
you will end up with all the full resistance. Here actually it's not actual resistance, it's resistance per inch, right? So you just add all this together, add all the resistance together, and then take a reciprocal. You will end up with U value.
Okay,
Maybe
okay, sir.
uh, anything else? You are doing your bachelor's, master's, Seema?
No, sir. I have done masters in environmental architecture.
Okay, okay,
Okay, and I am professor at DY Patil College.
fine, fine. So next week we will be looking into more about acoustics and also lighting.
Okay, sir.
You can any doubt related to this week like on sound, shading, or energy simulation? Sorry, the thermal performance simulation. In order to like you can actually these are like introduction. This acoustics basically is an introduction. You can look further into how to design rooms that will be covered next week, and also there are multiple softwares that are available. Acoustics basically uses a software, a popular software. Remember what it is? Odeon, ODEON, I guess. That is the software that is being used. And for thermal simulation, there are also open source simulation softwares which are graphically usable, like Open Studio, eQuest, all these things. And also this there is a free plugin with Rhinoceros. It's called Honeybee and Ladybug. These two tools together are used for building energy simulation. Yeah, I'll type it. eQuest, Open Studio, uh, Ladybug. There are very few software which are used for acoustic simulation. But just introducing to you, you can explore them. There are multiple. Actually, in India, there's not much scope related to like lighting and acoustics. Even there are, but when you go like abroad and all, there are like multiple consultancy firms which just dedicatedly work on acoustic solutions or lighting solutions. Next week when we look into lighting also have various open source softwares like Dialux, so what else? Dialux, and there is Diva for Rhinoceros. Even Design Builder has basic calculations. I have ANS decibel in practice assignment. Then my answer was wrong, so please confirm anybody. Practice assignment. Let me open. Practice assignment. You mean week 0? Okay, okay. Basically, here in week 0, they have asked sound pressure. Sound pressure is measured in pascals, basically. The decibel is, it means pressure level. When there is a word called level, you use decibels. I hope you get it. Yeah, thank you. So anyways, thanks for joining the session. Hope you join the last session. Next week will be the last session. We'll meet you there. Any other doubt if you have, please ask, or else I'll close this meeting. Okay then, thanks for joining.